Okay, this video is going to be about adding forces, graphical versus analytical. I'm going to have to be really quiet because there's a class next door. They'll think I'm going crazy. I'm talking to myself again. Anyway, we're looking at the idea of a graphical solution here. You need to remember, a lot of you are advanced math students and you're very keen on doing an analytical solution. Obviously playing to your strength is a very good thing, but some of these questions you can smash them out using analytical solutions very, very quickly. If they don't specify what type of solution to actually approach the problem with, if an analytical is going to get you to a solution quickly, do it graphical is going to get you to a solution very quickly, do it graphical, okay? So for this type of problem, it's very much like one of the examples we already did with the tractor to find a resultant. We have three forces. This is not drawn to scale. It's a free body diagram. F1 is 400 newtons, going straight up. F2 is 200 newtons, and F3 is 600 newtons. And we're trying to arrive at a resultant with a direction. Okay, so I haven't put my degrees in here. 45 degrees. 45 degrees, okay? So we need to get to a resultant. So all you need to do is specify a scale. So this is an analytical solution. That's shorthand for solution, okay? Very shiny at that point in the board. An analytical solution. Okay, so what we're going to do now is just specify a scale, because that's the first thing you need to do for an analytical solution. But we're going to say that 10 millimeters is equal to 100 newtons. So when we get our answer in millimeters, we divide by 10, and that will be the amount of 100 Newton units that we've got. Okay, so it's pretty simple. So we're going to draw a line going straight up, F1, and F1 is 400 newtons. 100 newtons. So it would be 40 millimeters. Okay, you don't have to draw the lengths in, but that's just to let you know that I've multiplied by units of 100. Okay, so there's 4 times 100. 100 is 10, so it's 40 millimeters. So because if I divide that by 10, I get 4. 4 times 100 is 400 newtons. Okay, I'm harping on about it, sorry. And then the next one we're going to do is F2, which is 200 newtons, which is going to be, instead of 40, it's going to be 20 millimeters. And what angle is that going to be at? We would get our protractor out, we would get ourselves a horizontal line. We would have made sure that this one was vertical. Then we get our protractor and we would put it on there. We would make sure that when this line comes up, it's half the length of this one, 2 centimeters, so it'd be 20 millimeters. I'm just going to put the distances in circle. You wouldn't have to necessarily write them in. It's probably a good idea to label the forces a bit. F1, F2, this is 45 degrees. And then we go straight across, because this F3 is horizontal. Okay? Straight across, and it's going to be 60 millimeters. F3 equals 600. Tip to tail. So we now have a resultant. Our resultant goes from our starting point. I'm going to draw a resultant. I'll get another colour. I might do it another colour. You've got the blue, the purple. We go from here, and if I had a ruler, it would be really good too, but I don't. So I'm going to do my best to get a line that's straight. Well, not really, but anyway, close enough. And then what we need to do is we would get our ruler out and we would measure that purple line, okay? And we would divide by 10 the measurement would be in millimetres. We would divide it by 10. That would give us how many 100 newtons we have, units of 100 newton that we have. And when we measure this, we end up with 92 millimetres, and we divide by 10, we get 920 newtons. So the force resultant equals 920 newtons, and we get our protractor out, and we would measure that angle with our protractor, physically measure it, and we end up with, I think it's 36%, 36 degrees, sorry. So we draw a line like that, and we go 36 degrees. And that's the analytical solution to example 2.3 in your textbook, okay? Get used to doing analytical. They're the bee's knees, okay? Don't reject this approach. It's a really good approach. It's a really quick approach. When we're doing 3 force problems, trying to solve them analytically, you'd be mad. Anyway, see you in the next video where we look at the analytical solution to this problem.